Hello, welcome to the channel Physics Cafeteria. So, today we are going to see the Born statistical interpretation. So, in the previous video, we have seen so far the primary introduction about the Schrodinger's equation and probability density. So, to continue this episode, or you can say the video, we are going to see the basics about the quantum mechanics and the philosophical discussion about the quantum mechanics. So in classical mechanics, everything is predictable. If we know the initial position or velocity of particle, we can calculate its entire future motion, right? And we have discussed in the previous video. But in quantum mechanics, certainty gives the way to the probability. A particle is no longer said to be somewhere. We can only speak of the likelihood of finding it somewhere. This new framework, the statistical interpretation, lies at the very foundation of modern quantum theory. Every quantum system is described by a wave function psi of xt. It's not a physical wave like sound or water, but a mathematical wave containing all the information about the system. Psi can be complex, meaning it has both real and imaginary parts, so it can't represent something physically measurable by itself. So what does psi tell us? Max Born proposed that the square of its magnitude psi of xt square gives the probability density of finding the particle at the position x at time t. This means psi square into dx represents the probability that the particle lies between x and x plus dx. So, this was revolutionary. The wave function doesn't describe a physical wave spreading through space, but the probabilities associated with the possible outcomes. Now we want to see some more details about the normalization condition. So, mathematically speaking, it says that integration from minus infinite to plus infinite of psi square dx gives you the 1. It has a physical interpretation. So if we are taking the space about minus infinite to plus infinite, then this suggests that particle is necessarily present at the given region. And if it is so, then this condition will give you the answer 1, and which is the maximum probability. Another condition we are going to have is integration from minus infinity to plus infinity psi square dx equals to 0, and that is known as orthogonalization condition. This condition tells us that no matter how much you try to find the particle or how much you try to figure out the probability, you'll get 0 because the particle is not going to be there. The third one condition we are having is that orthonormalization condition. So it suggests the particle may be there or may not be there. If it is there, it will give you the probability 1, and if it is not there, then you'll have to change your domain. You'll have to increase your boundaries. It may be out of your boundary, but you have to change your boundaries. So that is known as orthonormalization condition. So since the particle must exist somewhere, the total probability over all space must be 1. And this simple condition ensures that the wave function is properly normalized. It's the quantum analog of saying the particle must exist somewhere in the universe, right? So this is how we can certainly tell. However, we cannot define the position or the observations like the classical physics with the certainties. But in quantum mechanics, there is a game of the probability. And this probability is evolving with time. So that's why we can say there would be a flow of probability. As time passes, psi of xt evolves according to the Schrodinger equation. Even though its shape may change, the total probability stays constant. It just flows around like water in a pipe. The equation that is the continuity equation. It looks like a continuity equation, that is del by del t of psi square plus del j by del x equals to 0. This flow of probability means the evolution of probability with time. It's like at every point, probability is ranging from 0 to 1. So it's like a current and current density. So you see the same equation in fluid dynamics. This is how certainties will disappear. And now we are having the changing probabilities. We can say that probabilities which are changing with respect to time. So we have to expect several values for the several observables, and those values are known as expectation values. So expectation values come into picture to design the framework which is analogous to the Newton's law of motion. So here we are defining the total 3 types of positions. Okay, in the ensemblic interpretation, what does probability mean? Here's an important clarification. Psi square doesn't describe how a single particle moves through space. It describes the statistical spread of results you would get if you repeated the same experiment many times with identically prepared systems. Each particle gives one random outcome, but the overall pattern matches the probability distribution size. Now, let's come to these 3 philosophical positions, right? So, but how should we interpret this probability? There are several questions, like what is the true nature of the particle before we make a measurement? For decades, physicists debated 3 main viewpoints, and these three main viewpoints are known as the positions. So first is realistic position. The realists believed the particle really does have a definite position, we just don't happen to know it. According to them, the wave function merely reflects our ignorance about the truth but hidden reality. So yes, Einstein's view was God doesn't play dice. De Broglie's view was that was known as also pilot wave theory, and he suggests that the wave functions guide us, a particle which always has a real and definite position. And these views were about the certainties. What does Einstein mean at the time that God doesn't play dice? That means there should not be any uncertainties in describing the position of any observables of particles. So he was clearly believing in the reality, and he was surely telling the certainties about the particle. And on the other hand, we are having the second one type of position that is known as agnostic position. The agnostics say maybe the particle has a definite position, maybe it doesn't, and we will never know. Since it makes no observable difference, the question is meaningless. So quantum mechanics, they argued, works fine without worrying about what's really happening underneath. And here we can also put some questions, like can we even know what's the real beneath the math? Right? The third one is the orthodox position. The orthodox, or it is also known as Copenhagen view, championed by Niels Bohr, takes a bold stance. Before measurement, the particle simply does not have a definite position at all. It really is fully described by psi, a spread out probability wave. Only we measure do we obtain a definite value, and the wave function collapses to a sharp spike at the point. Until the 1960s, reality was very contextual. It depends on the measurement setup. Quantum mechanics doesn't describe what is, but what we can know. After all the hurdles, all these 3 views had their supporters. But in 1964, physicist John Bell shocked the world by proving that these interpretations aren't just philosophical. They make experimentally different predictions. Bell's theorem showed that if particles truly had pre-existing positions, as realists claim, then certain correlations would violate quantum predictions. But experiments since then have confirmed the orthodox interpretations. Particles do not have precise position prior to measurement. The act of measurement itself helps create the outcome guided by the statistical structure of the wave function. So, suppose we measure the particle's position and find it at point C. According to the orthodox view, the act measurement collapses psi into the sharp peak centered at C. If we immediately repeat the measurement, we'll get the same result because the wave function has already collapsed to that position. Over time, however, psi begins to spread out again according to the Schrödinger equations, restoring the uncertainty inherent to quantum systems. So in this total discussions, if I summarize it, we can say psi of xt encodes everything we can know about a quantum system. Psi square is a probability density, not ignorance, but fundamental indeterminacy. The total probability always equals 1, and the Bell's experiment confirms that the quantum world has no hidden classical reality beneath it. The act of measurement itself brings about the outcome, a strange but beautiful truth at the heart of quantum mechanics. So in the next video, we are going to see deeper the knowledge about the expectation values and some statistical aspects. We'll also see how these ideas lead naturally to the operator formalism, the mathematical framework that links every measurable quantity in quantum mechanics to an operator acting on psi. So stay tuned, and remember, in the quantum world, reality itself depends on how we look at it, right? Thanks for watching. Like, share and subscribe, and we'll also look for the next videos.